Good afternoon and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, it's problem time, where we answer chemistry questions. The topic for today is Lewis dot structures. Lewis dot structures are a simple way to try and conceptualize how the electrons within a molecule are distributed in order to create a stable species. And by stable, we generally mean that each of the atoms will have a full octet, that is, 8 valence electrons, either of its own or by sharing with other atoms. There is an exception to this, and that is hydrogen. Hydrogen only requires 2 electrons in order to be stable. Some larger atoms are also able to go above 8, and we'll see an example of that as we do these questions. Okay, let's get started. Let's start with a relatively simple question. Draw the Lewis dot structure for water. The way that I like to approach these questions is to think about how many valence electrons each atom has. So for example, hydrogen has 1 valence electron and oxygen has 6. I'm going to start by putting my oxygen in the middle. And I said that it has 6 valence electrons. So I'm going to start placing them around the atom, going at cardinal directions. What I mean by that is the first one goes north, then east, south, west, north, east, and now we stop because I have used up all 6 of those electrons. You can see that 4 of those electrons have been put into pairs, and there are 2 electrons on their own that are available for bonding. So each hydrogen has 1 electron available to bond. So if we were to put one here, it could make a single bond. And if we put one here, there'll be another single bond. Sometimes when I'm first thinking about these kinds of questions, I might use different symbols depending on whereabouts those electrons are coming from. So for example, if I do this again, I might go, well, my oxygen, and I might use little crosses to show its electrons, and then my hydrogen's electrons as dots. This is just a way to help think about where they came from. In truth, to say that this is the hydrogen's electron and this is the oxygen's electron doesn't make sense. And so this is the actual correct answer. And we see that we have a single bond between the oxygen and each of the hydrogens, and that there are 2 lone pairs. This next question is a little bit more complicated. We're going to draw the Lewis dot structure for carbon dioxide. Carbon has 4 valence electrons, and as we saw before, oxygen has 6. We're going to put carbon in the middle, and I'm going to do my 1, 2, 3, 4 dots around it. So I can see that it has 4 electrons available for bonding. If I do my oxygen, and I do this 1, 2, 3, 4, 5, 6, I can see that these 2 can easily pair up, but that doesn't satisfy oxygen's octet. It wants to get to 8. So I could move this electron in and that electron in and create a double bond. So it'd be a carbon, I mean 1, 2, 3, 4, oxygen, 1, 2, 3, 4, 5, 6. And we're going to do the same on the other side. So I'll get rid of this electron down there. And now all of the atoms have a full octet, meaning that they have 8 electrons around them. There are no electrons that are unpaired, and everything is stable. We have a carbon-oxygen double bond on each side. So we could also draw this like so. Now in this question, we're going to have to break the octet. And by that, I mean we're going to have an atom with more than 8 electrons around it. Sulfur has 6 valence electrons and fluorine has 7. So if we were to put our sulfur in the middle and start as normal, going around the cardinal directions, we'd get 1, 2, 3, 4, 5, 6, which only leaves 2 places to attach our fluorine, which we can easily do for those two. If there's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. But we still have 4 more fluorines to attach. So what we do here is we take this lone pair and we're going to separate those electrons. And now I can put a fluorine here, that's 1, 2, 3, 4, 5, 6, 7, and a fluorine here with 1, 2, 3, 4, 5, 6, 7. And we're going to have to do the same to this lone pair over here. And now we put in the final 2 fluorines. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So what we end up with is sulfur with a single bond to 6 different fluorine atoms. And each fluorine will have 3 lone pairs around it. So each fluorine atom has satisfied its octet rule of reaching 8 electrons, but the sulfur atom, it has gone to an expanded octet. It now has 10 electrons around it. And we rationalize this by saying that the sulfur could have hybridized in some of its empty d orbitals. And that's why it's able to go to this larger, higher expanded octet. If we have a charged species, then we either get additional electrons or fewer electrons, depending on whether it is a positive or negative charge. So in the case of this question, where we're asked to draw the Lewis dot structure for the hydroxide ion, we're going to get an extra electron. We're going to have the oxygen with its 6 valence electrons, hydrogen with its 1, and then because we have a -1 charge, we get an extra electron. So here we've got our oxygen, and we'll do our 1, 2, 3, 4, 5, 6. Hydrogen with its 1 makes a bond, and if we had to stop here, oxygen would only have 7 electrons. It wouldn't have reached a full octet. But we get an extra electron due to that negative charge. So we can put it in here, and now we have a full octet around the oxygen. Now, the way that I've been showing you to approach these questions is not the only way to do it. It's just my preferred method because it makes you think about how the molecules are bonding, why it is that these atoms are coming together to form those bonds. You can also do it in a more arbitrary manner. So for example, in this question, we're going to do the Lewis dot structure for the nitrite anion, NO2-. We start as before and we say, well, nitrogen had 5 valence electrons. Oxygen has 6, but there's 2 of them, so we'll multiply it by 2. There's 12. There was only 1 nitrogen, so that stays at 5. And we have a -1 charge, so that's going to add in an additional electron. And we can add all of these up to say that we have 18 electrons to place in our structure. Start by putting down the nitrogen and the 2 oxygens. Put a single bond between each of them. Each single bond uses up 2 electrons. So we had 2 single bonds, so that's 4 electrons used up. Let's subtract that from what we had over here. We now have 14 more electrons remaining. So we're going to start placing these 14 electrons as lone pairs, starting on the outside. Each oxygen can accommodate 3 lone pairs. This has used up 12 of our electrons. So we have 2 more, which we will put here on nitrogen. Looking at this structure, you can see that although the oxygens have a full octet, the nitrogen does not. So we're going to move one of the lone pairs in to create another bond. And this now gives us a final structure, where we have a double bond to one of the oxygens and a single bond to the other. And all of the atoms have a satisfied full octet. When you reach the end of a Lewis dot structure question, if there is any ambiguity about how the electrons could have been placed, then it is usually resolved by looking at the formal charge and picking the structure with the lowest formal charges involved. Also, notice that last structure we drew for the nitride ion, that had a double bond and a single bond, but we could also have drawn it as a single bond and a double bond with exactly the same formal charges. This brings up the topic of resonance, but that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a question you'd like to see answered in a future problem time, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.